Good morning. Welcome to fourth day lecture on design of RCC elements. Today we are going to see about doubly reinforced section. In last lecture we have covered what is meant by singly reinforced beam sections under working stress method. Then we have seen some analysis part and design part for problems also. Today we are going to see about doubly reinforced section analysis and with its problems. Okay, what is meant by doubly reinforced section? Doubly reinforced, in the name itself it describes you the reinforcement is provided in two ways, that is as double. In two ways is nothing but the main reinforcement you need in a beam section is only in the tension region, whereas you don't want any steel to be provided in the compression zone. Here, for some considerations, we have been putting steel in compression zone also. That's why we are calling it as doubly reinforced, that is the reinforcements to be placed in compression zone and also in tension zone. That beam is said to be doubly reinforced beam sections. Okay, what is the use of providing doubly reinforced beam sections? Why not we prefer singly reinforced sections? Singly reinforced is nothing but we are providing steel only in the tension region. When the load carrying capacity of the beam needs to be increased, in the same time we should not increase the depth for that beam. Then we need to carry over to singly reinforced section to doubly reinforced section. That is one criteria is restricting your beam depth is the main criteria for going for singly reinforced section. When you have heavier loads, to accompany your loads, you need to prescribe a small section. Also, we can go for doubly reinforced, or else for headroom consideration, we will go for doubly reinforced sections. So that doubly reinforced section, it will be economical. In most of the cases in our day-to-day life, we are using doubly reinforced sections in all our construction elements. That's why we are using doubly reinforced. Now we will see about the analysis part of doubly reinforced. Okay, I am drawing a section of beam of breadth B, total depth D. This is the beam having breadth B and total depth D. At the center we will have neutral axis. The depth of neutral axis is X here. The name itself doubly reinforced, that is we are providing steel at the bottom as AST, area of steel in tensile zone, whereas we are providing steel at the top, that is ASC, area of steel in the compression region. Till the centroidal distance, the effective depth will be small d. This is from the top to the centroidal line of the steel. Up to centroidal line of the steel, you can call it as the effective depth of the beam. Below this, you can call it as effective cover. Okay. What is mean by the centroidal line from the top fiber? This one you can call it as DC, you can call it as E into D. Okay. Now we are going to draw the stress block for this doubly reinforced section. How to draw the stress block? Here in the same way, this is your ultimate stress in concrete, sigma CBC, permissible stress in concrete under bending compression, sigma CBC. At the line of steel, you can draw a line. This one you can call it as sigma CBC dash. This is at the centroidal line of your steel in the compression zone. Then in the tension zone, sigma st divided by m. This is your ultimate. The force levels you can draw a, this is called as stress block parameters. You can draw a force for this. Here the total tension T here is equal to T1 plus T2, whereas here at the distance of x by 3 you will have a compression force C. Okay, now we'll write the description about these features. What we all know, B is breadth, capital D is total depth. Then what is DC? DC is nothing but depth of center of compression steel, that is equal to ED. Now you can call what is E? E is nothing but compressive steel depth factor. Then what is mean by sigma CBC dash? That is equal to, where sigma CBC is permissible compressive stress in bending compression, whereas sigma CBC dash we can call it as stress in concrete surrounding compression steel. Then AST, area of tensile steel, ASC, area of compressive steel. Here we can write MC. MC is nothing but modular ratio for compression zone, where M is nothing but modular ratio for tensile zone. Okay, from these diagram, this one A, this one B, this one C. From this stress block we can able to calculate the depth of the neutral axis. Now we can write sigma CBC divided by sigma CBC dash is equal to KD divided by KD minus ED. Now you can take it out the D values, so cancel it, K divided by K minus E. Or else if you want to find out sigma CBC dash, sigma CBC dash is equal to K minus E divided by K, K minus E divided by K into sigma CBC. If somebody is interested in finding out sigma CBC dash, we can directly calculate from this formula and you can directly write sigma CBC. This sigma CBC can be found out when M20 or Fe4 and 5 steel is given. We can directly calculate from the code book and you can calculate K minus E divided by K into sigma CBC. You can try to calculate sigma CBC dash. Okay, then stress in steel TC is equal to MC into sigma CBC dash, that is equal to MC into K minus E divided by K into sigma CBC, where MC is nothing but 1.5 times M. That's why 1.5 M into K minus E divided by K into sigma CBC. Okay. From the similar triangles of this diagram, sigma CBC and sigma ST. From figure B, sigma CBC divided by sigma ST divided by M is equal to, this is your X divided by the value is D minus X. That is X, you can denote it as KD divided by D minus KD. This one you can write K divided by 1 minus K, where K you can write the formula is as M into sigma CBC divided by M into sigma CBC plus sigma ST. This is the factor for calculating the design constants values. K is equal to M into sigma CBC divided by to sigma CBC plus sigma ST. Here, if you know these values, you can directly plot your value K here and you can calculate the sigma ST also. Okay. Now, next thing, how to calculate depth of neutral axis. Depth of neutral axis. To find out the depth of neutral axis, equating the moment of area about the concrete in the compression zone is equal to moment of area about the steel in the tension zone. Now, B X into X divided by 2 plus MC into ASC, that is in the level of steel you have MC times ASC into X minus DC. Okay, minus of, this is modular ratio of concrete in the compression zone. Okay, minus ASC into X minus DC, that is equated to M times AST into D minus X. That is the formula here, the tension zone, M times AST into this value is D minus X. This value is X minus DC. So B into X square divided by 2 plus MC into ASC, that is equivalent area of concrete is converted to the area of steel section in the compression zone minus of your area of steel is equal to, here you need to calculate the moment of concrete alone in this part. So that's why we are neglecting your area of steel present in your compression zone. Okay, right. Now you can able to calculate B X squared divided by 2 plus MC minus 1 into ASC into X minus DC, that is equal to M into AST into D minus X. From this formula you can able to calculate the X value, that is the depth of neutral axis. Okay, from this is the analysis over to calculate the design constants value. Here the extra design constants value when compared to singly reinforced beam is that E is nothing but a factor. In singly reinforced section we have calculated some factors, that is the lever arm factor J, then K. These are the two factors. Then from this factor X is equal to KD, Z is equal to JD. We can calculate from these two factors. Here DC is equal to E into D. This is the one more factor, the compressive steel depth factor. This is the one factor for doubly reinforced section. Okay. Now we are going to calculate the moment of resistance of this section. Moment of resistance for doubly reinforced beam. Okay. I am drawing the same beam B AST. This is the neutral axis. You have T is equal to T1 plus T2. The compression force will act as the distance of x by 3. Now, taking moments of compression zone about the center of the steel, tension zone, M is equal to B into half of x into sigma CBC will act at the distance of d minus x by 3, d minus x divided by 3 plus MC minus 1 into ASC into sigma CBC dash into d minus ED. D minus ED, or you can call as DC also. Okay. From this, we can directly calculate P divided by 2. For x, you can write KD into sigma CBC into d minus KD divided by 3 plus for 1 m, here you can write 1.5 m also minus 1 into ASC into sigma CBC dash into d minus ED. Here for KD you can write here 1 minus k by 3, you can write it as J. Now half J sigma CBC into, you can take d out, so B d square sigma CBC B d square, this k will be here k plus 1.5 m minus 1 into ASC into sigma CBC dash into, take the d out, 1 minus E. Now from this value we can write R, the resistance, moment resistance coefficient, where R is equal to half J K into sigma CBC. So this value. So you can write R B d square plus 1.5 m minus 1 ASC into sigma CBC dash into d into 1 minus E. Here this value we can call it as M1, where this is M, moment of resistance. For this value you can call it as M2. Now from this M1 and M2 you can calculate AST 1 is equal to M1 divided by sigma ST into JD. AST2 is equal to M2 divided by sigma ST into J into D minus DC. This is the two values, we can calculate it from M1 and M2. Now MC minus 1 into ASC into x minus DC is equal to M into AST2 into D minus X. From this also we can calculate AST2 is equal to ASC MC minus 1 divided by M into X minus DC divided by D minus X. You can write in this form also. Also you can substitute directly the X value if it is known, or else you can calculate it from K into D. This is the methodology to calculate the area of steel and moment of resistance for doubly reinforced sections. Okay. Here we have the same problem as divided as 3 sections. Here also we have balanced section, under reinforced section and over reinforced section for the doubly reinforced sections also. In the same way, you need to calculate the actual neutral axis for the given beam. Then you need to calculate the critical neutral axis section for the balanced section. From the critical neutral axis balanced section, you need to check your actual neutral axis value, whether it is lower or under. So that if it is over reinforced section, you need to take the formula for concrete governing. That is, for over reinforced section, first failure material is concrete, so you need to take up that formula to calculate the moment of resistance. Whereas for under reinforced section, the steel will be the first yielding criteria there, so you need to take up the steel formula, that is M into sigma AST. That formula you need to take out to work out your moment of resistance. Now we are going to see the problems related to doubly reinforced sections. Okay. We'll see one type of problem. Type 1. A beam 300 by 560 mm reinforced with 4 bars of 25 mm dia in tensile zone and 4 bars of 12 mm dia in compression zone. The cover to center of both reinforcement is 40 mm. Determine the moment of resistance. The moment of resistance of the section. Adopt M20 and Fe415. Okay. Now we are going to see about how to calculate the moment of resistance of a section for a doubly reinforced section adopting M20 and Fe4 and 5 from the codebook IS 456. For M20 we can write the design constants. Design constants for M20 is sigma CBC is equal to 7 Newton per mm square. You can see the permissible stress in concrete under bending compression value for the grade of concrete M20, that is sigma CBC 7 Newton per mm square. For Fe4 and 5 steel, sigma ST constant is 230 Newton per mm square. Then the modular ratio for M20 is 13.33. MC here 1.5 times 13.33. You can write 19.99. Say it is about 20. Then from the reinforcement given, you can write AST is equal to 4 into pi by 4 into 25 square 1963.5 mm square. We can write in compression zone AC is equal to 4 bars of 12 mm diameter. You can call 4524 mm square. This is your AST and ASC. Now calculate depth of neutral axis, that is x value. How to calculate the depth of neutral axis? We know the formula, b x squared divided by 2 plus mc minus 1 into asc into x minus dc, that is equal to m into ast into d minus x. Here when we draw a figure 4 bar, this is 4 bar, this depth in the problem it has given it as 40 mm, the same way here also it is 40 mm. So the depth of this bar 560 is the total depth, 560 minus your cover 40, that is 520 mm. Okay, 520 mm. So you can substitute the d value 520 mm. So you can calculate x. X is about 210.4 mm. Now you can calculate the critical neutral axis of balanced section. XC is equal to m into sigma CBC divided by m into sigma CBC plus sigma ST into D. This one you can get 150.1 mm. 150.1 mm. Here the x value is 210. Now the actual depth of the neutral axis is 150. This 210 is going beyond this 150. So your concrete will be the governing area here. Okay. Now sigma CBC dash is equal to sigma CBC into x minus dc divided by x. You can get 5.669 Newton per mm square. Now you can calculate MR. MR is equal to B, that is 300 into 210.4, that is your x value. This is your B value into 7 divided by 2, 520 minus 210.4 divided by 3 plus 20 minus 1 into 452.4 into 5.669 to 520 minus 40. You will get MR as 122.77 into 10 power 6 Newton mm. These are some of the types of problems related to doubly reinforced section. One type of problem maybe you will get how to calculate the depth of neutral axis of your section. So you can equate the moment of compression area to moment of tensile area to calculate the x value, or else the question may be like this: how to calculate the moment of resistance of the section. After calculating the depth of neutral axis, you need to check whether it is over reinforced or under reinforced section. Then you can proceed with your moment of resistance section, to which formula you should take. When you know whether it is under or over, you will take, this is XC is 210, whereas the actual neutral axis is 150, so the section is over reinforced. That's why I preferred the formula as concrete formula. Okay. Then the problem may be, everything will be given, you need to calculate the AST value. Moment will be given, then directly you can calculate AST is equal to m divided by sigma ST into JD. You can directly convert those formulas. These are some of the problems related to doubly reinforced sections. Okay, let me conclude this lecture. We have seen what is meant by doubly reinforced section, where we will use doubly reinforced section, then what are the analytical part over doubly reinforced section, and one thing mainly I want to give you here is the neutral axis depth is not mainly depends upon your steel present in your compression zone. It does depend upon your presence of steel in your tensile zone only. When you change your amount of reinforcement in compression zone, you don't have any problem for your depth of neutral axis at all. Okay, the depth of neutral axis will change depends upon your tensile steel. When you increase your area of steel in the tensile zone, it will be moving upward or it will be moving downward based on your section designed it as under reinforced or over reinforced. Okay, these are some of the factors you need to remember for your doubly reinforced sections. Tomorrow we'll see about limit state design of structures. Okay, thank you.